right. Hello, everyone. Welcome to CS292F. This is the fifth lecture. We're going to be talking about subgradient today. So can everybody hear me well? Okay, great. Let's get it started. Before it, just a reminder that the homework one is due tonight, midnight. And if you need extension days, like everybody have a budget of, I think, 4 or 5 days for extensions. So you can use it for any homeworks. It's a total of that budget is a total number of extension days for all 4 homeworks. So use it wisely, and there will be no penalties for the extension. And also for that reason, since there will be people using their extension days, please hold your discussions about the detailed solutions to your homework on Piazza until after a week from now. So everybody would have submitted their homework. This is just to ensure the fairness of the evaluation of the class. And now that everybody is remote, and it takes the effort of every individual to ensure the fairness of the class and to ensure that you do not take away the learning experience of any of your peers. All right, let's get it started on the lecture. We're going to be talking about subgradient today. Before that, as usual, let's have a quick recap of the materials that we talked about last time. So last time it was the first lecture that we talk about concrete algorithms. So we talk about solving the unconstrained optimization problems with F being convex and differentiable, and in addition, we can make some additional assumption about the smoothness of F in the form of the Lipschitz constant of the gradient being bounded by a constant L. And under that condition, then we talk about how this particular algorithm, this very simple algorithm, is that iteratively updates the parameter x by moving towards the negative gradient direction. Okay, and we showed that when the step sizes t are chosen to be fixed and small, or chosen adaptively using line search techniques, then this procedure will end up converging to the optimal solution at certain rates. Okay, so one question that for those who are familiar with machine learning and optimization for deep learning, to have in mind is that since the backtracking line search is such a powerful technique, why aren't people using it? Why are people still hand-tuning the learning rates of their favorite optimizers like stochastic gradient descent or Adam optimizers in deep learning? What's the difference? I guess the answers are twofold. First of all, so we're talking about gradient descent. We're not yet touching upon the stochastic gradient descent yet. Where this gradient is a stochastic approximation of the. Yes, there were 2 answers from students. One said in the chat box, one said it's non-convex, the other said it's too costly. Well, non-convex may or may not be a good reason, as we talked about last time. For non-convex problems, as long as locally satisfies the Lipschitz condition, we can use the backtracking line search to obtain a learning rate such that it satisfies the sufficient descent condition. It's a little bit trickier, but you can do that as you keep decreasing the learning rate as long as there are enough enough of a slope. Even if you are non-convex, you can still find something that move you sufficiently lower. And the second question, the second answer is too costly. So that's really the reason. For stochastic gradient descent, you only have to randomly select, say, 1 data point or a mini batch, a random subset of data points, and then evaluate their gradient. If you think about backtracking line searches, it requires you to evaluate the objective function value, and it requires you to use a full gradient. right? So log 1 over epsilon iterations of backtracking line search would mean that you go over the data set for that many times. So that turns out to be not really feasible for really large scale optimization problems where you have many data points. So that's something that we're going to be revisiting in the next couple of lectures after we talk about the exact version of the gradient descent and proximal gradient descent, and then we'll start talking about the stochastic approximation and how we can like solve the similar optimization problem a lot faster with respect to the size of the data set for machine learning problem. Okay, yeah, excellent answers. So last time we also talked about the computational guarantees. So for objective functions that are L smooth, or often also known as L strongly smooth, then the gradient descent with appropriately chosen step sizes have a complexity of order L over epsilon. So again, this is iteration complexity. It measures the number of iterations it takes for you to reach an epsilon suboptimality solution, epsilon suboptimality ball, which means that the final iterate of your parameter satisfies the condition that its objective function value is at most epsilon away from that of the optimal solution. An alternative way of writing the same thing is to use the so-called convergence rate, where k is the number of iterations. So this is saying that epsilon is on the order of L over k. So it goes to 0 at a rate of 1 over k. So for any such convergence rate that is polynomial in k, in polynomial in 1 over k, we say that this is the so-called sublinear convergence rate. And if we make one additional assumption that the function f is m strongly convex, this means that the function is lower bounded anywhere by a quadratic function with identity Hessian, with identity Hessian scaled by a constant m. So if the function f is strongly convex, then we can establish a faster learning rate, faster convergence rate that goes to 0 exponentially as the number of iterations gets larger. So this is in the form of 1 minus m over L bracket to the power of k. And in this case, so m over L. So this is in the standard linear regression setting. So this is also the ratio between the smallest eigenvalue and the largest eigenvalue of the covariance matrix, and that gives us the condition number of the problem. One over the condition number kappa of the problem. So in other words, you can write the learning rate to be 1 minus 1 over kappa to the power of k. The convergence rate. So when they converges geometrically to 0, so we say that this algorithm satisfies the linear convergence rate. So from sublinear convergence rate to linear convergence rate, the improvement is actually exponential. In addition, if we just convert it to the other representation called iteration complexity, then what we end up getting is a logarithmic factor, a log 1 over epsilon, where epsilon is the desired suboptimality that we wanted to achieve. And basically, whenever we spend L over m or proportional to the condition number of the problem, number of iterations, so that more or less shrink the suboptimality gap by a factor of e, where e is the e constant e of the natural log, like 3.27 something. Okay, so finally, we also talk about the linear convergence of functions that are not necessarily strongly convex. They are not even necessarily convex. So we talk about functions satisfying the so-called PL condition, this Polyak-Lojasiewicz condition, and which is a weaker condition than strong convexity that in some sense bypasses the requirement of convexity. So when any function satisfies the PL condition with parameter m, then we showed that it converges at a linear rate with the same coefficient 1 minus m over L to the power of k. Okay, there are similar conditions to PL conditions that applies to convex functions and non-convex functions, such as error bounds conditions, the quadratic growth condition, the restricted secant inequality, and the associated restricted strong convexity conditions. So all these conditions are more or less equivalent when F is convex. So they are arguably the weakest possible condition for linear convergence of gradient descent. Okay, so so last time we also talked about last time we also talked about we stated this particular theorem, saying that with strongly convex functions f, the gradient descent algorithm converges exponentially with c to the power of k, and there's actually a gap in the proof that we had with the current given statement. So I don't know if any one of you guys noticed this glitch, right? So the way that we prove this theorem is by proving a slightly stronger result on the PL condition, in which case we establish that if we choose the parameter, the learning rate t to be smaller than 1 over L, then we can end up achieving a linear convergence rate with parameter c equals to 1 minus m times t. So when we choose t to be large as possible, this recovers this 1 minus m over L. On the other hand, like this learning rate that's stated in the theorem is actually bigger than the largest allowable in the theorem that we've proven, right? So is this theorem true? It turns out that this theorem is true, and we can actually take t to be as large as 2 over m plus L. The only the only difference is that that this only holds for strong convexity, but not for the PL condition. So so there is a more refined analysis that they can use to recover like the requirement that only requires t to be smaller than this slightly larger number, and with that you are able to establish a very similar linear convergence rate, but with a constant improvement. So for this choice of the learning rate, you can achieve a slightly smaller c that are bounded away from 1 by a larger constant, and you can convert this complicated nuking term into something that depends only on m over L, so or L over m. So this will be kappa minus 1, kappa plus 1 to the power of square. So this will be 1 minus 1 over kappa, 1 plus 1 over kappa square. So notice that this can be larger. Sorry, this can be smaller than 1 minus 1 over kappa that we established with the learning rate t chosen to be 1 over L. Okay, so looks like the color of this pen is a little bit weird. So let me change it so that next time we'll change it. Okay, okay, works. Okay, good. Okay, just one last thing. So we briefly mentioned Nesterov acceleration when we talk about whether the computational guarantees of gradient descent can be improved or not improved, right? So Nesterov established this lower bound, saying that for any algorithm that makes use of only first order information, so the family of algorithms are called Krylov space methods, which operates in a linear subspace spanned by the sequence of gradients that's obtained with a sequence of parameters that your algorithm turns out discovers. So it turns out that there are like better algorithms than simple gradient descent called accelerated gradient descent. So we didn't talk about how that works, and we didn't talk about the algorithm nor its analysis, but we can understand it as though from the complexity point of view. So for L smooth functions, there is an algorithm called Nesterov accelerated gradient descent that can achieve the faster iteration complexity by taking a square root of L over epsilon. So in some sense, this converges at 1 over k, L over k, and the accelerated gradient descent converges at L over k squared. Okay, so that can be a lot faster than simply taking L over k. Similarly, for strongly convex function, a version of Nesterov acceleration allows us to improve strictly over gradient descent as well. So instead of depending on L over m, so now you can again take a square root. So the dependence on the condition number of the problem can be significantly better than the standard gradient descent. Okay, so a quick question to you guys, and you can just write your answers in the chat box and respond to it once I see them. So since accelerated gradient descent dominates gradient descent, why the heck are we learning gradient descent at all? Like why don't we just directly learn accelerated gradient descent? And since that's the algorithm that has a faster rate, like shouldn't we prefer that algorithm always over gradient descent? Right. So that's a legitimate question. Because like since you have something that's better and it's something that's very similar to gradient descent, doesn't really suffer from any additional complexity in either space or time. So why don't we just only teach accelerated gradient descent? Yeah, so there were two answers. Answer from Alex saying that our functions are not always like L smooth. That's a legitimate question. Yes, gradient descent may work in cases when the functions are not necessarily always L smooth. Actually, we're going to be talking about a family of such problems in today's lecture, but only in the next lecture we'll be talking about the generalization of the gradient descent that actually achieves similar convergence rate, like for those family of problems. But similarly, we also talk about the gradient descent convergence in non-convex problem. Accelerated gradient descent turns out to be more reliant on the convexity condition. So if you are using gradient descent to optimize a function and you are not sure whether the function is going to converge, then the gradient descent will still always like converge at the rate, but it only converges to the to say a stationary point with guarantees. On the other hand, if you use accelerated gradient descent, then it may potentially diverge. Similarly, for strongly convex functions, the accelerated gradient descent requires a very delicate choice of the sequence of learning rate and specific parameters that's needed for the algorithm that requires knowledge of the strong convexity parameter M and strongly smooth parameter L. So without knowing these parameters, it isn't really easy to optimize over that family of functions with using accelerated gradient descent. And any bad choice of this learning rate will be more delicate, have a more delicate impact for accelerated gradient descent because it may potentially diverge. But for gradient descent, it is easy. We just have to set the learning rate to be sufficiently small, and we can use backtracking line search and so on. Okay, yeah. So this relates to Boyan's answer on accelerated gradient descent requires actual conditions. Like it doesn't, but we do. It is worse in the sense that we cannot more easily adapt to unknown parameters. Okay. So so today's lecture is going to be about the subgradients. So we're going to be talking about a family of new mathematics from convex analysis that will allow us to solve a much larger family of problems in convex optimization. So we're going to be talking about the definitions of subgradients. We're going to give a lot of examples. We're going to be talking about properties of the subgradients and how do we generically calculate the subgradients using components of functions that are composite from other functions. And also, we're going to be talking about how we can use subgradient to characterize the set of optimal solutions for convex optimization problems and also for non-convex optimization problems. Okay, so because of this, since we're going to be talking about crucial mathematical underpinning of subgradients, it's only until the next lecture that we'll be talking about concrete algorithms called subgradient descent and proximal gradient descent that makes use of subgradients to solve like possibly non-smooth optimization problems without the universal upper bound on the gradient smoothness, the strong smoothness parameter L. Okay, and another thing is that since we didn't get to talk about the gradient boosting example from the previous lecture, so I trust that many of you have already read that part of the lecture. So there are a couple of slides that we may go over if we got extra time towards the end of today's lecture. So if not, it's fine. I'm just gonna be like giving instructions and pointers towards gradient boosting on Piazza. All right, so subgradients. Yeah, but by the way, like please remind me if I forget to get you guys to take a break at 1:50. All right, so when it hits 1:50 and I'm still going on and on and on, and then please just unmute yourself and remind me that it's time to take a break. All right. Okay, so let's start from something that we know, right? For convex and differentiable function f, so the following inequality is the first order characterization of a convex function. So this is the first order definition of a function f being convex. And notice that we have the gradient there. So this is saying that if we extrapolate linearly for any point x and do the linear approximations, then it is always the lower bound of the convex function f. The subgradient is just a simple generalization of this first order condition that does not require function f to be differentiable. Okay, so the subgradient of a convex function f is one that always satisfies that if G is G is a subgradient at x, then for all y, fy is lower bounded by the linear approximation at f of x with a gradient G, with a direction G. Okay, so it can be shown that for convex function f, the subgradient exists anywhere. And if f happens to be differentiable, then notice that this G, there could be multiple G at that satisfy this condition at any given point. But if f is actually differentiable at this particular location x, then we know that the only G that satisfies this condition is a gradient. So you can think about subgradients as a generalization of the gradient in particular for convex functions. So notice that the definition of subgradient also extends to non-convex functions. So basically, for any function f, if we can write this inequality for all y at location x, then we say that the G that satisfies this condition at x is a subgradient of this function f at x. Okay, the catch is that for non-convex functions, subgradients are not necessarily a non-empty set at all x. So maybe for some x, this the subgradient exists, but for other x, non-convex functions do not actually have a subgradient. So that's part of the reason why when people talk about subgradient, it's usually for convex function. But it's important to notice that the definition of the subgradient extends to non-convex function as well. Okay, so let me start giving a couple of examples. So let's start from a one-dimensional function, the absolute value. So for all the x where the x is not 0, say at this point, the function is actually differentiable, right? So we can clearly see that the gradient is pointing towards this direction. So in other words, pointing towards this direction. So the gradient is just a sign of x. Similarly, like when you are over here, then the gradient is pointing towards this direction. The only part where the function is not differentiable is at the origin, is at this point. Okay, so so the set of all the set of all subgradients that satisfy the condition is a set of I guess the convex hull of this point +1 and -1, which gives us the any element from -1 to 1. Okay, so why is that? So notice that when we change this g, this local approximation, okay, so this local approximation, when we adjust the g from -1 to 1, then it changes from these. And as we decrease g and suddenly become these, when we adjust, when we set g to be 0, then it gives us this line. So for all these linear approximation of this function at f equals to 0, all of them are valid lower bounds of this function absolute value. That checks the condition, the definition of subgradient. Okay. So let's now generalize the conclusion to a higher dimensional space. Let's think about a norm rather than absolute value, right? So let's consider the Euclidean norm, which again, for people who don't remember what this is the sum over I from 1 to n xi square, and then you take the absolute, you take the square root on the outside. Okay, so for a two-dimensional example, you can visualize this. You can visualize this function as the surface of this function as something that looks like the shell of a cone. Okay, so again, when x is not at 0, then this function is differentiable, and then you can directly differentiate with respect to this using standard calculus. And then that will give you the unique gradient, and that's also the subgradient here. When x is actually 0, right? When x is actually 0, then you can think about any half spaces that support this function from below. For instance, you can take this gradient to be 0, then it becomes the x1, x2 plane at f x equal to 0. That will be the valid linear lower bound of this function at 0. And but it could be anything else. So this f of x could be any z transpose x when z satisfies that these two norm are smaller than 1. Okay. So how about we change the norm into into one norm? So let's change the geometry so that we get something that's slightly different. So now it becomes the absolute value, the sum of absolute value from 1 to n. Okay. When xi, notice that this function decomposes over the coordinates. So it suffices for us to consider each coordinate separately when we take the subgradient. Like we'll have like a more general conclusion about the statement just now a little bit later. So if we look at this the visualized function of the x1 norm in 2 dimensions with x1 and x2. So immediately you notice that the non-differentiable point of these functions are not just the origin. So there are also all these ridges where the function is actually not differentiable. right? So see that this is a flat, and then suddenly there's a suddenly there's an infinite curvature where this flat suddenly changes into something else. So this function is piecewise planar or piecewise linear. Okay, so for each coordinate separately, if it happens that this coordinate is non-zero, then the corresponding subgradient, the coordinate of the subgradient corresponding to that location is a sign of wherever you are. Like for instance, if you are here, then x1 is greater than 0, x1 is strictly greater than 0, and x2 is strictly greater than 0, then we know that the only gradient is pointing upwards towards this direction. Okay, so it is 1, 1. So for any coordinates where you satisfy this xi is equal to 0, for instance, if you are here, then both x1 and x2 is 0, then the corresponding gradient is any element in -1 to 1 from that location. So we will have a more analytical and algebraic illustration of this absolute value function in the slides to come once we talk about the subgradient calculus. Okay, for now, let's just build intuition by thinking about having a flat and having a half space that supports this function from below, and what those half spaces can be. In particular, if you are on this ridge, then any half spaces with the decision boundary that is that is changing from the flat that's facing you to the flat that is opposite towards the far end are going to be valid supporting hyperplanes of this of this function from below. Okay, so now like another important family of functions that we can talk about are the pointwise maximum functions. So we've already seen from the convex function part of the lecture that when we take the maximum, the pointwise maximum of multiple convex functions, then the final function that we end up getting is also going to be a convex function. And so let's consider the cases when both functions f1 and f2 are differentiable and convex. It is a maximum that suddenly creates the non-differentiability points over here. Okay, so when we take the pointwise maximum, then what is the corresponding subgradient of f of x? Okay, so when you are in the region where one of the functions and only that function applies, say in this region, when this is f1, so this is when you evaluate the subgradient at say x equal to -1, and this is a part where only f1 applies, then clearly in this case the subgradient is equal to the gradient, right? Similarly, if you add here, then the g is equal to the gradient of f2 of x. The only tricky part is when this function is non-differentiable. Okay, so when you are at here. So notice that the two gradient direction at this point are either this one or that one. Okay, so when these functions are equal, that means that both functions are applicable here. Then we can already see that if we need to construct a linear approximation that supports this function from below, then it can be any convex combinations of the gradients, any convex combination of the gradients between these 2 points, which says that the g is inside G is any point on the line segment between f of 1 to gradient of fx. So I'm abusing the notation a little bit. This actually means that the for all f1 x plus t gradient of f2 x minus gradient of f1 x for t in 0 and 1. Okay. Since they can be like a multi-dimensional object. Okay, so we've talked about subgradients, and we've talked about in many cases, especially when the function is not smooth at isolated points. So on those points, the subgradients are not unique. So subdifferential is a related concept that characterizes the family of subgradients at each location. So we are using this partial note, just a generalization from the the calculus, where we use this partial to denote the partial derivative or the gradients. So in this case, the subdifferential of a function f at location x is a set of all subgradients that applies at location x. Okay, so notice that the subgradient is one such one such vector that satisfies the definition of the subgradient condition, and subdifferential is a set of all subgradients at those locations. Okay, so it can be shown that from the existence of subgradient that this is non-empty, provided that the function f is convex, and we can also see that the subdifferential is a convex and closed set. And this is true even for non-convex functions. Provided that they exist, then they are closed and non-convex. Like you can also define the empty set to be closed and convex, which is trivially true. So that's why you don't have to specify whether the subdifferential exists or not exists. And if in addition, if f is differentiable at x, then we know that the subdifferential as a set is actually a singleton. And this is a set that contains only one point that's given by the gradient of f at x. And this is actually a characterization, because a converse is also true. If you can prove that the subdifferential is a singleton, there's only like one point in the set of subdifferential, then you can show that f is also differentiable at x, and the corresponding gradient is equal to the only element in this set of subgradients. Okay. So this is like one way that you can show that for certain non-trivial functions, that those functions are actually differentiable. So there are many functions that it's not directly intuitive why they are differentiable using elementary calculus, but with the use of subdifferential, like sometimes we can show that certain functions that are not obviously differentiable is actually differentiable for the large part of their domain. So we will see one example towards the end of today's lecture. So subgradients are closely connected to convex geometry through the so-called indicator function that we defined earlier. So again, this indicator function with this capital I denotes that if the input x is inside a convex set C, then you get 0. Otherwise, you get positive infinity. So and we've seen that the indicator function is closely related to the concept of a normal cone of a convex set C, right? So it turns out that if you evaluate the subgradient of the indicator function, you end up getting the normal cone. So that's how there's a interesting connection between indicator function and normal cone that we've seen before. So just recall that the definition of the normal cone is the following, then we've worked out in depth that how a normal cone is closely related to the first order optimality conditions in the case when we are minimizing a differentiable function subject to a convex set constraints. Okay, so let's see why. Let's see why the subgradient of the indicator function is a normal cone by applying the definition of the subgradient. So notice that this is the definition of the subgradients. Okay, if we can find a G that satisfies this condition, then that certifies by definition that G is a subgradient of this given function. At this in this slide, we are taking this function to be the indicator function with respect to a convex set C. Okay, let's discuss two cases. Since we need this to hold for all y, and so let's discuss two cases and whether y is inside the convex set or y is not inside the convex set. So y and by definition, when y is not in the convex set, then the indicator gives us like the positive infinity. So notice that this is on the left-hand side of the inequality. So no matter what the right-hand side is, then this inequality is always true. Okay, so that checks one leg of the discussion. And for the other leg, we have y inside this convex set C. In this case, the left-hand side is 0. Okay, in this case, the left-hand side is 0. And then how about the right-hand side? So for the right-hand side, when x is inside the convex set as well, then clearly we get 0 larger than 0 plus G transpose y minus x. When we switch this, when we just take the G transpose x to the other side, then we end up recovering the definition of the normal cone. So all the G's that satisfy this condition is in the normal cone. Okay, so how about when x is not in C, right? So when x is not in C, so we don't really have a G such that this is always true for all y, because we can take y to be inside the convex set, in which case we have 0 larger than positive infinity plus G y minus x. This can never really be true for all y, right? This can never really be true. Therefore, we know that when x is not in C, then the subdifferential of IC of x is actually the empty set. Okay, so let me know if you're not following this argument. In other words, so this when we talk about the normal cone, we talk about normal cone being only defined at those x such that x is in C, right? So this gives us an extension of the normal cone, which says that the n of C of x is equal to empty set if x is not in C. Yeah, and this is the a pretty self-consistent redefinition or extension of the normal cone, so that you can apply them more generally to all input x. So again, we can see this from we can clearly see this from this illustration that we have early on about the normal cone, right? So what this is saying is that what this is saying is that for the indicator function on this convex set, whenever you are inside this convex set, then the subgradient subdifferential is actually just a zero, or the sub. Okay, so this is intuitive because the indicator function, say in 1D, looks like the following. in 2D with x2, x1, right? In indicator looks like the following. You have 0 here, and suddenly outside this region, everything else is positive infinity. Okay, so you can see that if you are inside this region, then the only half spaces that supports everything from below is G equals to 0. And what this normal cone characterization is what this is saying is that on the boundary, the situation is a little bit different. So on the boundary, then you can work with you can work with any hyperplanes such that as long as this G is in the normal cone, so that gives you this and that. And at this non-differentiable points, it can be it can be a convex set of all G. So for any G that's inside the normal cone at this location X, is going to be a valid subgradient of this indicator function. Okay, so let's maybe summarize a little bit of all the examples that we have and abstract it away so that we can we can talk about the calculus of subgradients. And for many functions that we don't want to work out the subgradients all from the basic definition. So it is more convenient that we if there are many rules that we can apply so that we can more easily derive subgradients for functions like composite functions, for those like the sum of two functions. If each one of these functions has an easy to derive subgradient, then maybe we can write down the subdifferential more easily. Okay, so so here are a set of rules. So first of all, if you have a non-negative scaling of a convex function f, then you can exchange the order of that scale a with a subdifferential operator partial. Okay, so can anyone like comment on why the heck do we need this alpha to be larger than 0? Okay, I'll let you have a little thoughts on it. So on the second bullet point, when we have like two convex functions that are in a summation form, then we can essentially evaluate the subdifferential of each function separately, and then use it to construct the subdifferential of the whole thing. So since this is a set and this is also a set, we need to use a set addition called Minkowski addition. So set A plus set B is equal to x plus y subject to x in A and y in B. So this is set addition. Okay, so essentially in this case, if you work out the subdifferential of f1 and subdifferential of f2, then the subdifferential of f1 plus f2 correspond to taking any element from set partial f1 and any other set element from set partial f2, and then just add them up. And any such choices of elements from both sets would give you a valid element of the subdifferential of f1 plus f2. More generally, we can do the affine composition of functions with a convex f and affine ax plus b. So notice that this is one of the rules that we use that preserves the convexity, right? If f is convex, then substitute any affine arguments into the function f, will retain its convexity in a final argument x. Okay, so how about the subdifferential of this function g? So this is a rule that we can use more or less as if we are doing the chain rule for the standard calculus. So essentially, you are taking the subdifferential of f and ax plus b, and then you are multiplying a transpose in front. Yeah. So this is say f of, if f happens to be differentiable, then we can apply the chain rule, and that gives us a transpose a gradient of gradient of f evaluated ax plus b, okay, over ax plus b. There's I guess one last bullet point before we go to our break. So we talk about two functions when we take the maximum of f1 and f2. This can be naturally generalized to many many functions and many finite functions. Let's say that you have m convex functions f1 to fm, then the subdifferential of the composed function is a convex Hall of the union of all the subdifferential of f1 to fm at the locations where each one of these each one of these functions that we're maximizing over actually attains the objective value. So notice that we had this example previously, and this is argmax, right? So this is saying that at this location where both function intersect, then both function would apply. Then this would be, and then the subdifferential at this location would be the convex Hall of this vector and that vector. Okay, and at either these 2 points, then this condition will simply give us a singleton, because only one of these functions apply. All right. So one cautionary note about this addition, about this addition rule, is that this is like a set operation, and the rule that whenever we take like one individual element from the subdifferential of f1 and another element of subdifferential of f2, and then add them up, that recovers one particular valid subgradient of f1 plus f2, that is always valid without additional conditions. But suppose we want this equal to hold, we need to prove the inclusion on the other direction. And that actually requires some additional technicality. So a useful assumption, sufficient condition that one can remember is that provided that the intersection of the interiors of the domain of f1 and f2 are not an empty set, so provided that you can find at least one point within the relative interior of the domain of these two functions, then we can write that for those points, these two sets are actually equal. Okay, so I won't be going into additional details on this technicality, but because they are less important and less relevant for convex optimization, for those who wants to figure out the exact condition under which you can cap this characterization, like please refer to the Rockefeller's convex analysis book. Okay, so we'll take a 5 minutes break and we will resume at 2 o'clock. Yeah, meanwhile, for those who have questions, please post your questions on the group chat, and so I'll respond to those questions as I come back from the restroom break. All right, there are several answers to the questions that I posed earlier on what happens when A is smaller than 1, right? So all of your answers are right. So when you take A to be negative, then A of F is no longer a convex function. Then sometimes it doesn't really make sense to talk about subgradients because the subgradient may or may not exist. And for in fact, for concave functions, the subgradients almost do not exist anywhere unless it is a part where I guess unless you have a linear function. So there is a question about logistics on homework submission. So so we have 4 extension days in total. So the question is, how do we use the 4 extension days? Do you need to declare like you want to use the extension for a particular homework? So I'm going to make it flexible, so you don't have to declare that at the time of submitting the homework. So you can just submit the homework at like whenever they are ready. So at the end of the quarter, so you can decide like how you want to allocate the extension days over all the homeworks. So for instance, for one of the homework, you get a little bit higher grades than the other homework. Then in that case, you can maximize your grade by choosing how do you allocate those 4 extension days. Okay, so hopefully that's clarifies the question. All right, let's resume on the lecture, and we'll give more examples of all these. So we talk about scaling, addition, affine composition, and finite pointwise maximum. So we can generalize the finite pointwise maximum to the slightly more general form, which we can take the maximum over an infinite set. Okay, so in this case, if we take S instead of over just a set of indices, we can take S over an infinite set. Then it becomes more technical, but we can still write the condition such that we can always say that the convex hull of all the functions that satisfies all the functions that are active at this given x. If we just take the union of their sub differential and then takes the convex hull of that, and finally takes the closure of that convex set, basically to make it a closed and convex set, and then the whole thing, any point within this set is a valid subgradient of the pointwise supremum. On a couple of additional regularity conditions, again, like for those regularity conditions, and for people who happen to run into them and needed to use them for your research, the Rockefeller's book is the right reference for all these technicalities. So so on the additional regularity conditions, then we can write the inclusion on the other direction. So we can characterize the subdifferential of f of x for the pointwise supremum. Okay, so so I wanted to give a number of useful examples for the pointwise maximum and pointwise supremum, and then work out the details. So in particular, we're going to be working with the set of all vector norms and all the p norms. So again, the definition of this p norm is the sum of x to the power of x absolute value to the power of p over all the coordinates, and then to the power of 1 over p. Okay, you take the 1 over you take the p's roots of this summation. So that gives us norms, and for this important cases are p equals to 1, p equals to 2, and p equals to infinity, right? That correspond to the maximum, the Euclidean distance, and the sum of absolute value. Okay, so we can write this. We can write these norms in some sense in a dual form. So we can write them as pointwise supremum of a set of linear functions. Okay, so let's suppose there's another parameter q that satisfies the condition 1 over p plus 1 over q is equal to 1. Then that says that the p norm and q norm, they're conjugate with each other, or like one is a primal norm, the other is a dual norm. So example of this is that when p is equal to 1, the corresponding q is equal to infinity. And when p is equal to 2, the q is equal to 2. In which case we say that the Euclidean norm or any Hilbert space norm, they are dual to itself. And when p is equal to infinity, q is equal to 1, right? So this is actually like how we can define the dual norm. And notice that this is a pointwise maximum form of linear functions linear functions in X. So for any fixed z, this is a linear function in X. Therefore, when we take the pointwise maximum, it gives us a convex function. Okay. And in addition, the arguments that achieves the argmax gives us the subgradients. So this is an interesting observation. So we'll give two examples of these, okay, by writing in a board. Okay. So I guess the first example that we're going to be given is the L1 norm. Okay, so let me make it a little bit bigger. Okay. L1 norm. This is when p is equal to 1. Okay. So in this case, f of x is equal to max of s inside -1 to 1 to the power of n s transpose x. Okay, so notice that this is slightly different from what we've shown in the previous slide. That says s is inside inside the norm ball satisfies infinity norm smaller than 1. So why can we argue that these are equal? So notice that whenever we pick any u that's in the interior, we can always make it larger. We can always make it larger so that those points in the interior of this L infinity ball becomes less relevant. Right, so we can always make it closer to the boundary such that the S transpose X is larger than suppose S is in the interior. Therefore, it suffices for us to consider just -1 and 1. In fact, we know that this value is also the same as the sine of x multiplied with x. Okay, that gives us the x absolute value. Okay, so let's now calculate the corresponding subgradient of the absolute value function, the sum of absolute value function. So first of all, notice that let's apply the first rule so that we can decompose it into x1 absolute value plus x2 plus xn. Okay, so this is saying that this is saying that the subdifferential of this we can write it we can derive it on per coordinate for every coordinate separately. So let's say that the this is equal to J1 plus J2 multiply Jn, and these are Cartesian product. Which gives us a which gives us a set that's in R to the n. Okay, so so we'll discuss like several cases. So for each k, okay, so if xk is equal to 0. What does it mean? It says that the coordinates the case coordinates subgradient needs to be like can be anything from -1 to 1, because it doesn't really matter like what number that we take, because it's multiplied with a 0. We can set it to be anything. If xk is positive, then the subgradient of the absolute value function, we can basically drop the absolute value function and it becomes differentiable, and the subgradient is the same as the gradient, and that gives us 1. And if xk is negative, then similarly we get -1. Okay, so I'll visualize it a little bit more. So so let's take n equal to 2 so that we can visualize more geometrically, and then the subgradient of say 0, 0. So this will be the product of -1, 1 with -1, 1. So if this is x1, this is x2. What this is saying is that the subgradient is the whole set in this box. Okay, and suppose we have say 0.50, then this is saying that you get a set that's just 1 multiplied with -1, 1. Okay, in the second case, this gives us a line segment at x1 equal to 1, and x2 can be anything between +1 and -1. Therefore, this line segment is the set of all subdifferential at 0.50. So how about 0.1 minus 0.1? In this case, we get 1 minus 1. Okay, and that's and that's just a singleton, and that's just a singleton right here. Okay, so let's now give another example of L infinity norm. In fact, like let's generalize it a little bit. So I'll leave the L infinity norm as an exercise. Let's give another example. So the previous example, so even though we started off with a pointwise maximum with an infinite set, but we showed that it can be reduced to a finite set because because S needs to be in a box constraints, and it only suffices that we consider all the vertices of that box. Okay, let's now consider something that's actually a pointwise supremum when we are maximizing over an infinite set. Let's consider something that's peculiar, that fx is the largest eigenvalue of a given matrix A of x, given like symmetric matrix parameterized by x. So let's define AX to be A0 plus x1, A1 plus xn, an, where aj for all j is Rn by n, and aj is equal to aj transpose. Okay, so this is a set of linear matrix inequality style construction of this matrix AX. So AX is a linear combination, is an affine combination of a set of n+1 matrices with coefficient vector x. Okay. So make sure you can think about like these objects in matrices space. Okay, so by our definition of the largest eigenvalue, and now that this AX is symmetric, we know that all the eigenvalues are real. Okay, and then we also take the eigen decomposition of A of x, so it suffices, like, so it makes sense to talk about the largest eigenvalue. So in particular, we can write f of x to be the supremum of all vector y such that y is smaller than 1 and y transpose A of x, y. Okay. So first of all, can anyone tell me that why the heck is this function convex? What is a rule that we learned previously in a composition of convex functions, or like some rule about convex functions that we can apply here to show that this weirdly nuking function is actually a convex function before we even start deriving its subdifferential? Yeah, anyone who wants to answer, you can unmute yourself, or you can just enter your like short answer, or maybe pointers and thoughts in a group chat. So a little hint is that this is in the form of a pointwise supremum. And we talked about pointwise supremum of convex functions are convex. So there's an answer from the group chat saying that maybe an increasing convex function of convex function is still convex. So could you clarify that a little bit? An increasing function of what? What is the argument that needs to be convex here? And why is it increasing? Yeah, there's another answer that's closer to what I have in mind. So there's a question, there's an answer saying that can we use the fact that A of x is affine? Well, yeah, A of x is affine in x for sure. But the function that we talk about is y transpose AXY. So actually this is about the right answer. So let's think about each function y transpose ax f. So this is a function that's parameterized by g, but it is ultimately a function of x. Okay, so we wanted to show that for any fixed y here, that this function is convex in x, right? So it's really easy to get confused, and then try to think about whether this function, this quadratic form, is convex in y or whether it is convex in x. But all we need is actually this thing is convex in x, not y, right? So since for y, this quadratic function can be either convex, concave, or neither convex nor concave, we don't really know how to talk about it at all. But suppose we just write this gy of x function explicitly by substituting this into the definition of ax, we get that this is equal to y transpose a0 y plus x1, y transpose a1 of y plus x of n, y transpose a n of y's, and each one of these are scalars. So we end up getting something of this form, c transpose y, which is a linear, which is a linear function in x. Okay, so yeah, excellent answer. So now that we've shown that this function f of x is convex, so now let's derive its subdifferential by applying the rule of pointwise supremum. Okay, so so let's derive what this partial of fx is. Okay, so notice that the first thing that this is a closure of the convex hull of the union of all all fy indexed by y of x. In fact, this is g union of all g y of x is equal to f of x. And then we can take the subdifferential of g y of x. Right? So since fx is the maximum over all y, satisfying that y's norm is smaller than 1, the corresponding set of argmax, the arguments that achieve this, are those y's that are eigenvectors corresponding to lambda max, right? So then the evaluation of the subgradient becomes easy. So algorithmically, the first step is to find eigenvector of a of x, and let y be any eigenvectors with eigenvalue lambda max of a of x. Okay, and the second step would be to construct the corresponding gradient. So the gradient would be y transpose a1 y, y transpose a2 y, y transpose a n y. So why is that? Because this is the gradient of a g y of x at location x. Okay, so that gives us a valid subgradient of this complicated looking function f of x at any given location x. Okay, and if we want to get the full set, then you just find all eigenvalues that correspond to eigenvalue, all eigenvectors corresponding to eigenvalue lambda max, and then you take the span of the subdifferential of f of x would so this would be the inside the subdifferential of f of x. So the subdifferential would be the convex hull of all such y union of all such y transpose A1 y transpose A n y. Okay. I hope this example makes it convinces you that it is often useful to work with pointwise maximum, and sometimes you can use it to do really fancy stuff and then derive gradient for functions that will otherwise do not know how to derive the gradient or the subgradient. Okay, so so there are two reasons why we care about subgradients. So first of all, it's like gradients just doesn't seem to be sufficiently like sophisticated that allows us to describe the class of all convex functions. Therefore, subgradients plays a central role in convex analysis. And in particular, it allows us to characterize the optimality of convex optimization problems using just subgradients and with a very simple condition that we'll talk about in the next slide. Okay. Subgradients are also useful in convex optimization because as long as that we can computationally compute and construct one particular subgradient for any given point, then we can use a gradient descent style algorithm to minimize any convex function. So notice that these convex functions even include those with indicator functions. Therefore, like this is just more general than the standard gradient descent or the standard subgradient descent for unconstrained problems. So today's lecture is going to be focusing more on the first part, and then we'll be talking about the algorithms and iterative algorithm called subgradient descent in the next lecture. So first, let's talk about optimality condition. Okay, so take any function f and let x star be the minimizer of this function. Okay. So it can be shown that, like, regardless of whether this function f is convex or not convex, then fx star is a minimum objective function value is equivalent to say that zero is in the set of subdifferential at x star. In other words, like the subgradient or subdifferential can be used to certify any given solution is the optimizer or not the optimizer. Okay, so this is an if and only if condition. Okay, so we call this condition the subgradient optimality condition. So how do we see this? So it's actually very straightforward. It straightforwardly follows directly from the definition of the subgradient. So notice that the definition of subgradient saying that G is a subgradient at x if for any y, f of y is larger than f of x plus G transpose y minus x. But notice that if 0 is inside the subdifferential, then we can substitute this G to be 0. Right, so once we substitute this G to be 0, this is saying that for any y, then f of y is larger than f of x star. So that gives us the exact definition of x star being optimal. Right, notice that we haven't used convexity at all. So this is like a very general, although pretty trivial characterization of the set of optimal solutions for any optimal solutions. And in fact, like if the function happens to be convex and differentiable, and then using the condition that we had previously, that the subdifferential is a singleton set that consists of only the gradient, by just saying that this is a generalization of the gradient of fx equal to 0 condition that we've seen previously for unconstrained optimization problems that are differentiable. Okay, So we can also make use of subgradients to derive the first order optimality condition using a slightly different argument. Okay, so recall that the first order optimality conditions that are fully general for minimizing differentiable functions with solutions constrained to a convex set can be written as this this inequality. So if the gradient at location x satisfies this normal cone constraints, then this says that x is optimal. Okay, so we can derive this like using subgradient and subgradient calculus by casting this constraint set as an indicator function. Okay, let's work it out and then apply the subgradient optimality condition. So first of all, 0 is inside here, inside this, and then what does it say? Notice that f is differentiable. So and also f is differentiable and unconstrained. Then there is one interior point inside the convex set C that allows us to apply the additive condition of the distributed rule of this subdifferential. So this is saying that this is equal to f of x plus the partial of IC of x. But this is f is differentiable, so we can just write this of f of x plus partial IC of x. Okay, if we move this to the other side, so this basically tells us this basically tells us a minus gradient of f of x is inside the partial IC of x. Okay, but what did we say previously about the subgradient of indicator function? So previously we've seen that the subgradient of the indicator function is actually the normal cone of C at x, which gives us the gradient is inside the negative gradient is inside the normal cone, right? And then but by substituting the definition of the normal cone, you recover exactly the first order optimality condition. Okay, so that will be a proof that comes directly from the subgradient calculus. Okay, so so yeah, I've also written this down here, and you can follow these lines of equivalence to show that the first order optimality condition is equivalent to the subgradient optimality condition in the cases when f is differentiable here. Okay, so notice that both these conditions are fully general for differentiable function f. However, since we're not making it explicit what this constraint set C looks like, like these kind of conditions are only of limited practical usage. So later when we talk about the KKT condition and talk about the optimality condition written down like more explicitly with the different constraint sets in the standard convex optimization form, with a set of inequality constraint and a convex inequality constraint and a set of affine equality constraints, then that kind of characterization become more and more useful for all the practical use cases. Okay, so we'll see more of that later when we talk about KKT condition. So let's give a couple more examples, and then let's try to apply the subgradient optimality condition to derive an interesting set of conditions for lasso. Okay, so again, this is the regularized version of the lasso where we are penalizing the one norm of the coefficient to induce sparsity in a way that's convex. Okay, so let's work out the subgradients. So first of all, by applying the rule of subgradient and using the fact that the first part of this objective function is differentiable, then we can simply get the first part being the gradient and the second part being the subdifferential of partial of the one norm of coefficient vector beta. Okay, so this is equivalent to say that if we move the gradient to the other side, okay, this is equivalent to say that the negative of the gradient of the loss function is equal to lambda times v for some v, for at least some v that's in the set of subdifferential. Okay, so what we have seen about the one norm, the subdifferential of the one norm, is that it can be decomposed into individual components. So we have seen that when for coordinate I, if beta I is positive, then we get the then we get 1. If beta I is negative, we get -1. So these two can be grouped together, saying that the Vi is equal to sine of beta I. Okay, and the interesting case comes when the beta I is actually 0. So when some coordinates are shrinked to 0, then we get the full set between -1 and 1. Okay, so this will be the set of all Vi. So the question is that whether we can certify like whether a beta is optimal by finding whether there exists a particular Vi that satisfies these conditions. Okay, so when we write it down in full, so that is basically saying that the condition that this quantity for there exists a particular V satisfying these conditions such that X transpose Y minus X beta is inside this set can be evaluated for every coordinate separately. So let's go over those coordinates. And for those coordinates where beta I is not 0, then we have this exact linear system of equations, which says that this is exactly the same as lambda times the sine of beta I. And for those beta i's that are 0, so we need the solution beta to satisfy the condition that the absolute value of these need to be smaller or equal to lambda. And in fact, if we can show that this is strictly smaller than lambda, then that implies that the optimal solution beta I needs to be 0. Okay, so that allows us to sometimes prove like certain coordinates of the solution needs to be 0 even before solving the optimization problem, and that's used a lot in sparse recovery techniques such as lasso in compressive sensing, and in fancier constructs such as sparse subspace clustering, where we wanted to do like the dimension reduction and clustering at the same time. So some of the analysis pioneered by Candice et al. In Annals of Statistics were later extended to robust version by me and my co-author. Okay. So the key technical results that's in these results are nothing but just the subgradient calculus. So you can derive everything from elementary subgradient calculus and use them to show under certain models on how the data is generated and with what kind of probability that over the distribution of the data that the final solution may recover certain structures that are desired. Okay, so when we consider a simpler version of lasso, yeah, so I missed a question from previously. There's a statement saying that it is a normal cone at X. Yeah, sorry, I forgot like whether that that answer is responding to which question. But yeah, I guess I'll get back to it like towards the very end if we have time. Okay, or offline on PS. So when we specialize the lasso problem to the case when the design matrix X is identity, then we get the simpler optimization problem that decomposes to each coordinate. So notice that this can be rewritten as a sum of I from 1 to n, yi minus beta I square plus lambda beta I absolute value. So it suffices that we solve each coordinate separately, and by by plugging in the suboptimality condition, so again, so this becomes minus 2 times beta I minus y. These two got canceled. Is inside the lambda subdifferential of beta I. So by doing this, we get the subgradient optimality conditions that looks like this quantity. Okay, what this quantity is saying is that you can use the so-called soft thresholding operator to have a one pass of the coordinates and then figure out the optimal solution to this simplified lasso problem. In particular, for those y that are larger than lambda, then we know that for those y's that are larger than lambda, then we know that for this condition to be true, then beta must be bounded away from 0. Therefore, we can evaluate the right-hand side to be simply the sign of beta. In particular, if y is larger than lambda, then that implies that beta I is strictly larger than 0, and which allows us to evaluate the right-hand side, which says that this is lambda, and then we have minus beta I minus y is equal to lambda, which says that beta is equal to y minus lambda. Okay, that gives us the solution here. And similarly, when y is smaller than minus lambda, then we get this. Okay, so what if y is in between? When y is between minus lambda and lambda, then the only solution for beta 0 that applies is beta 0 equal to 0, because which says that minus y needs to be lambda of inside the lambda of beta I. Okay, since y is unspecified, it can be anywhere between minus lambda and lambda. This needs to be a set. It cannot be just a singleton, right? And the only case when this is a set is when beta I is equal to 0, and therefore when y satisfies this condition, then we know that the optimal solution for that coordinate is beta I equals to 0. Okay, so that gives us the so-called soft thresholding operator. So the reason why it is soft thresholding is because we're thresholding at lambda, but we're doing it in a pretty soft way. So when y is larger than lambda or smaller than minus lambda, we're not keeping wherever y is to the solution, but instead we're shrinking it a little bit towards 0 by a margin of lambda. Okay, so this turns out to be very useful as a part of the optimization for solving lasso using the so-called proximal gradient descent, which we'll talk about. We'll be talking about next in the next lecture and the next lecture after that. Okay, so visually, the soft thresholding operator looks like this. So the input is in the horizontal axis, and this is plotting only one of the coordinates, and the output is given in a vertical axis. So whenever you are at here, then you're shrinking it a little bit by shrinking it down from when the input is here, your output is shrinking it by a factor of lambda. When you are negative, then you are pushing it up by a factor of lambda. But when you are in between, then you are basically outputting 0 like throughout. Okay, so so I guess the last thing that I'm gonna talk about today is to give yet another example to build some additional intuition about the subgradient self-step differential. Okay, so let's work with this this distance to a convex set function. Let's say that we have a fixed convex set C. Okay, and the distance to the convex set is the distance between the input x to the point y in the convex set that is closest to x. In other words, we can rewrite this to be x minus the projection of x onto this set C. Okay, so so intuitively, like this is a pretty complicated function which involves the minimization of a bivariate function. Can anyone like just type in a chat box and tell me like why does this distance to a convex set function necessarily a convex function in X? Which rule like are you applying from our convex function set of lectures to argue this with just one line? Anyone? No takers? Okay, let me prove this for you. So so first of all, y minus x to norm. So this is a convex function. To norm is a convex function, and y minus x is an affine transformation of the vector xy. Therefore, this thing is jointly convex in x and y, right? And then since we are minimizing this function over a convex set, then this is partial minimization. So by applying the rule of a partial minimization, yeah, there's an answer, Zhongming, like excellent. So that's exactly right. You are doing partial minimization of a jointly convex function and eliminate one of the variables, and ultimately you are getting a convex function. Yeah, but from the shape of the function itself, it's unclear like whether this function is differentiable or not differentiable, or whether at different regions, whether it is differentiable or not. Okay, so in this example, we'll show that this function is actually differentiable when x is such that the projection of x is greater than 0. So the distance from the convex set is greater than 0. So this should be pretty intuitive, right? So think about a line segment in 1D. So from A to B. Okay. So the distance from this set, the distance from this set would should linearly upwards, right? So in these regions, when x is such that the distance to this convex set is strictly larger than 0, it should be clear that this is a differentiable. This is a point where the function is differentiable. Okay, so the only part where this function is not differentiable is on the boundary of this of the convex set. Okay, so so we're going to be looking at the subdifferential of this distance to convex set, and it turns out that the subdifferential is can be shown to be a singleton set. And if you can show that, and using the if and only if condition of the differentiability, you can use this to prove more generally for any convex set that at these points that this distance function is actually differentiable. Okay, so we're only going to be showing like one direction of this statement. Okay, so in particular, that means that we're going to show that this is a valid subgradient by checking the definition of the subgradient. Okay, so let's work with this projection notation and then define this shorthand using this additional parameter u. Okay, and by the first order optimality condition, we can write that x and u satisfy this inequality. So how do we see that? Okay, so u is an arc mean of okay, and then if we just take the gradient of this, the gradient of this would be 2 times u minus x, and by first order optimality condition, we know that for any y, it satisfies that this is larger than 0, right? And now let's multiply -1 on both sides, and that gives us x minus u transpose y minus yeah, sorry, this is y, since we're talking about u, right? And x is an input, so this is optimality, first order optimality condition. This is smaller or equal to 0 for any y inside the convex set C. Okay, that gives us this. Okay, so now let's relax this a little bit. Let's talk about the half spaces that's given by this notation H, right? Let's consider the set of all y such that this inequality holds without restricting itself to y is inside this convex set C. Okay, let's consider the set of all y that satisfies this inequality. So notice that this is a half space because y is the only thing here, and this is and this gives the normal of this half space, and this inequality is choosing just one side of that affine half space. Okay, so we'll be proving that this inequality, saying that the distance from this alternative point y to C is larger than whatever that's on the right hand side for all y. Okay, so for now let's live with this, and then it will be clear like why we want to prove such a thing like momentarily. Okay, so in order to prove this, there are two things that we wanted to discuss. First, we want to discuss when y is inside this convex set C and when y is not inside the convex set C. Okay, and yeah, actually, when y is inside the convex set H or not inside the convex set H, and if y is inside the convex set H, then this inequality is easy to prove. And that's because, like, by the definition, the right-hand side is always non-positive. Okay, so that gives us this inequality right away. So it suffices to prove the case when y is in H complement. Okay, so when y is not in H, then notice that this inner product can be rewritten as the 2 norm of that multiply with the cosine of the angle between these two vectors. Okay, between these two vectors. And then when we write this down, we can cancel this x minus u 2 norm with the x minus u 2 norm in the denominator, which gives us y minus u 2 norm multiplied with this cosine angle, right? And what is that? Right? Suppose you have this half space, and you have this y that's right here, and notice that notice that u is some point here, right? So y minus u multiply with the cosine of theta actually gives us the projection of y onto this half space. Onto this half space H. Okay, and since that H is a larger set than C, since H is C is contained in H, then the projection into H has a distance that's much smaller than the projection of y onto C. Therefore, we can upper bound this distance of y to H, and using the distance of y to this alternative convex set C. Okay, so the convex set C is here. Since this projection of y into the H might not be inside the C, therefore, like this distance is necessarily smaller or equal to y, the projection of y onto this convex set C. Okay, so by using this claim, then this allows us to prove the statement in the previous slide, right? Okay, so now let me tell you like how to use this claim to actually show that the desired property that x minus u normalize it with this norm actually gives us a subgradient of the original function of interest. Okay, so the trick is to just minus x and plus x. So let's subtract x and then add x back. Okay, and once we do that, if we combine these two terms and then divide this, we end up getting rid of this square term. And what remains is x minus u divided by x minus u norm transpose y minus x. Okay, and that's and notice that this x minus u is simply the distance of x to C, since u is defined to be the projection of x to C, right? And then this checks the definition of subgradient directly. This shows that G is the subgradient of the distance of x to C at x. Okay, so I hope that that's a clear argument that everyone's able to follow. Okay, so so just now we've shown one subgradient of the distance to convex set function at any locations that's outside the convex set. I'm leaving a few like open questions for this particular function of interest. So it's useful to work with. So recall that previously we've given this one-dimensional example of a line segment, and this distance to the convex set when C is equal to line segment AB looks like the following. So from this, we can already tell that this function is differentiable in places that are outside A and B, and it is also differentiable in places that's between A and B, right? But on the boundary of this convex set is not actually differentiable. Okay, so I'm leaving 3 quiz questions like for those who wanted to answer them on Piazza. So the first one is that how do we prove the converse by showing that this is the only subgradient for all those x that are outside the convex set. And the second quiz is for those x that are inside the convex set, and how do we work out its subdifferential? Okay, and then answer the question that generically, how do we generalize from this one-dimensional convex set that distance to any convex set inside the convex set is differentiable, and outside the convex set is differentiable, but on the boundary they're not actually differentiable. Another thing that I wanted to you guys to work on is to consider instead of the distance in the Euclidean distance, maybe let's consider this function, which is more or less equivalent, but with an additional square here. Okay, without the additional square, like can be look at the question of differentiability with a little bit more details, and then argue whether the final function that we're getting is actually differentiable. All right, so that will be the besides the homework, so those will be the quiz questions that for you guys to think about, and I guarantee you that when you work out these quiz questions, and your understanding of subgradients will be a lot deeper than suppose you do not. And hopefully this will also help you to work on questions in homework 2. Okay, so that will be the end of the lecture, and thank you guys all for your patience. And I will be, I guess, giving a little bit of pointers on the gradient boosting example on Piazza like later today. Yeah, thank you very much.